Okay, cool. So the last lecture we talked about dynamic programming approaches for RL. This time we're going to talk about Monte Carlo approaches. So Monte Carlo just means like throw the dice, like you were in Monte Carlo at a casino, if that makes any sense to anybody. Again, I should call out just these resources I've used for these lectures, the Lillian Wang blog post I talked about last lecture, as well as lecture 3 of CS234 from Stanford. So in the Monte Carlo case, or let me start kind of take a step back, right? Like in the dynamic programming case, we were talking about evaluating a policy directly against its value function or state action function pair, the state action pair function or the Q value. The what if we don't know the world? What if we don't know the result of a particular action and how it affects our state and how that affects which reward we get at which transition and so on. We have to sort of start to use experience. We start to have to kind of look at the environment and try different things. And Monte Carlo is one such way, right? We can essentially model our value function as the expected return, and this is sort of we can recall this expectation definition of the value function. And so instead of now evaluating the value function based on this world model, we can just sample the environment. So instead of actually using the world model to create a probabilistic distribution of all the different possibilities of things that may happen, we're just going to try. We're going to have a set of different episodes that we can then see how things went, and we can sort of average them. And that is what's called Monte Carlo sampling, or just taking random samples of the world. Now, you can kind of hear one of the limitations as I talk about it this way, which is, well, if we need multiple episodes to get a sort of estimate of what may happen in the world, we can only really apply this to what are called episodic MDPs, meaning we have to have episodes that have a start and an end. If you have a problem where you can't die, right? If the agent can't end, we can't hit a termination state, then it's pretty difficult to sample the world because you need multiple episodes for this to work. So with that limitation, let's dig into how this works. So there's a variety of different Monte Carlo policy evaluation processes, but we're really going to just talk about a couple of different variants in that. So you can kind of think about this first one as being the base case, which is first visit Monte Carlo policy evaluation. In this case, we kind of keep an active count of how many times we've seen a particular state, and we also keep a sort of average of the return seen at that particular state. And so first off, we start off, we initialize everything to 0 for all possible states. Keep in mind, you can kind of see already, we need to have some knowledge of states in our MDP. So this is still dealing with the tabular form of reinforcement learning where we know what our states are. But that's for a different time. And now we sample a particular episode. And by that, we are going to sample a state, an action, then we're going to get a reward, we're going to get a new state, and then we're going to take another action, and we're basically going to run our policy, right? We're going to take an agent, put it into this environment, run our policy, and keep track of the states that we've seen, as well as the returns that we've seen. And for every particular state, we're going to define this return for that particular state as essentially just calculating the sum of discounted rewards that we've seen at that particular time step. And we're only going to deal with it the first time that we see that state. So if you have like a cyclic MDP, I think this is why this particular evaluation algorithm has the name first visit, is because the first time you see that state, you calculate this, and if you see it again, you leave it alone. It's just going to be the same thing. And then, but we still kind of keep account of how many times we've seen that particular state. And then we just do that the first time, and then we update the estimate, right? and that's going to be the number of the return that we've seen divided by the number of times that we've seen that state in our Monte Carlo sampling process. I think I might have kind of made this not been very clear. So the number of times we see the state is going to be across episodes, not within episodes. So we only increment the number of times we've seen a state one time for any given episode. And so what we're doing is averaging the return that we've seen at that particular state over all episodes, right? So that's what this G of S divided by N of S is referring to. And so this is actually doing nothing more than just calculating frequency of the number of times we see a particular state and how much that state has been worth to us. So yeah, it's a little bit tricky to calculate this because you can kind of see like we need to keep track of the returns that we've seen at that particular state onwards. So there's a little bit of trickery to get this coded up correctly, but that's all we're doing. We should know this, right? When you terminate, you know all the different states that you've seen, and then you ascribe value to them in that way at the end of the episode. So yeah, pretty straightforward, right? You're just keeping a track of you sample the episode and then you do this processing on it because by the time you're like the first step is running your agent in the environment, blah blah blah, but then you die in the environment and now you have all this data and you go through the data and you calculate these statistics on the data. So it's not some wonky thing. It works every time. It's just keep in mind that you're retracing your steps. So like the value of a particular state is based on the rewards you've seen from that point on, but in the context of your data, you're going backwards in time. So that's a kind of an interesting gotcha if you're going to implement this. So you can already sort of imagine, well, what if we dealt with every time if you have a cyclic thing and you hit this really valuable state multiple times, you kind of want to integrate that into your policy evaluation. And so there's also a variant called every visit Monte Carlo. So you also kind of handle the situation where you run into a state multiple times. It's very similar, right? You ultimately sample your episode like we did before. We define that return in the same way as a return from time t onwards in the episode. And now instead of just the first time we come across a state, we do this every time we come across a state. So, state S is going to be the state visited at time step t in episode I. So now we increment the number of states, and this is done every time. And we increment the total return like that, and then we divide it. So we're actually, this kind of counterintuitive in a way, right? Because we're now averaging the total return for the number of times you've seen in a state. And so this is, I think, a good place to kind of think about your problem, right? If your problem is one that being in a state multiple times is okay, then every visit's not going to hurt you, right? But if your problem is one where being in the same state multiple times is not a good thing, then actually you want to use every visit versus first visit, right? Because in first visit, you're only going to say I go to a particular state the first time and I get a reward of 10, but the second time I get a reward of 0, and forevermore. It's almost like finding a treasure. You can only find the treasure one time. So if you come back to the treasure chest and you've already taken the treasure, it's empty. So what are you going to do, right? So in that case, every visit's good because we're going to get penalized. If I go back to the treasure the second time, now my expected reward goes down because now I'm dividing the reward of finding the treasure by 2 instead of 1. But in the first case, in the first visit, I can go back to that treasure as many times, but as long as I saw a reward the first time, I'm still going to expect that to be a high value state to be in. So you can kind of see the sort of subtle difference between every visit and first visit. Incremental is sort of a bit of between, right? We sort of increment this based on this this sort of like more I don't know how to describe it, but we let me go through the algorithms, right? It's the same idea as before. We sample a particular episode. We define all of the returns for each of the states, respective at the time step, and so on. And now for each state, every time we come across that state, we increment a counter, but then our value function is weighted by the number of times that we've seen that state. So the idea being here, right? The first time I see a value, the first time I come across a state, this value is actually going to be 0, right? Because it's going to be 1 minus 1 over 1, which is actually 0 over 1, which is 0, right? So our state's going to be explicitly just the value of the particular state is just going to be exactly equal to the return. However, if I come across a state a second time, now we're dividing the value by 2, but yeah, like multiplying it by 1/2, and same thing with the return. But you can kind of see that if we see a state an infinite number of times, then eventually this converges to the value of just being equal to a value, because this turns into 1, and this becomes infinity, and so now you're kind of transitioning the values function from the value that we've determined for that state versus the reward that you've seen in that particular episode. And I guess the right version of this equation is a little bit better, where you can sort of see this as a bit of a baseline. The baseline meaning we take the value of our state that we know and we add to it, and this is divided by the number of times that we've seen that particular state, the difference between the return and the value. So you can kind of imagine if we see a higher return this particular episode than our expected value function of the state, we're now adding. If it's below, then we're subtracting, right? It's sort of like trying to in a way, if you're familiar with the idea of an exponentially moving average, this is sort of what's happening here. So we have this idea of a baseline, which we'll see again very soon in some of the future, the next techniques that we use. And now we're kind of trying to average out to getting to that average. We're trying to get this baseline of the return minus the value of that particular state. We want that to be 0, right? And so in the early days, when we've only seen the state once or twice, we're going to be aggressively changing our value estimate. But as we have higher and higher knowledge, right, as the number of times we've seen that particular state goes to infinity, eventually this baseline goes to 0 just by definition of one of that being the case. So we're essentially trying to kind of create this incremental adjustment to our value function as we see more and more data related to that particular state. So this is kind of a nice medium between the first visit and the every visit, right? This is sort of helping us learn over time what we should expect. So in the beginning, high fluctuation or high variance, but over time, lower variance, and hopefully still, no bias. So just to kind of recap, right? We learn these complete episodes to completely compute the return of a particular episode, and now we essentially can compute this mean of the value function in using just greedy, as we talked about before, or just greedy. In fact, we can define a new policy based on the action or the action given a state that we would take to maximize this Q function, and we can then estimate a new Q based on these values. So that's kind of it for Monte Carlo, right? You're just sampling the world and seeing what happens, and then you're updating your policy according to your new set of value functions. So next, we're going to talk about temporal difference learning. So we're going to take that idea from the incremental Monte Carlo, this idea of a target, and we're going to start to kind of play with that. Can we do things that allow us to enter into model-free learning without a episodic constraint? So let's talk about that in just a second.